got the idea. I'd love to hear you talk about where you got the idea. Brilliant. So what are primitives? Primitives are things that validate their input arguments and either succeed and perform some operation, which is returned as a result of the method, or they fail without side effects. One egregious violation of this is the load and image technique, where if it fails, it numbs the image technique. Try and undo the damage. But basically it's true. And when I came to the code in the VM, there were only 4 examples that I had to rewrite. And these are examples which install semaphores, which look like, okay, if the thing on the top of the stack is a semaphore, install it. Otherwise, assume it's nil, and nil out the semaphore. So the symptom would be that the system would lock up if you installed nil, if you look at the forwarding pointer, and that was a semaphore. So those 4 primitives have to be written to nil. If the object on the stack is nil, then you install nil. Otherwise, it's a semaphore, otherwise fail. So, okay, here's a cursor. And a cursor is a subclass of form and has bits, which is a pointer system. Obviously, bit data, a width small integer and a height small integer, a depth small integer, and an offset, which is a point. We'll have an x small integer, like here, a y small integer, might have a float, we might have a fraction, in which case, the primitive, when it tries to consume that information, will be tracking for a small integer, and if it's not a small integer, it will fail. And then there's a map. So we've got the image, and then we've got the state around the image, which is another 4. Again, has bits, and then there's width and depth, and then there's the offset. So the precursor primitive is like one of the more complicated ones in the system. Has to validate its input to depth 2. That's it. Depth 0 from the stack, and then it goes depth 1 into the offset, and the form, and then depth 2 into the offset. And it checks that all of the objects have the right track before it continues. And forwarding objects don't have the right track, so it always fails. So it's not a problem. So what you have to do is you have to find out the depth to which each primitive traverses its input structure. Right? And follow the input structure to that depth if the primitive fails, look at the forwarding primitive. If you find the forwarding primitive, you fix them up. And if you found any, you can infer that the primitive failed because it failed validation because it found the forwarding object. And you can just retry the primitive. So that's exactly what. Yes, we need to pound on it, but so far it's been working really well, and it's really so gentle. Put a bag over that now, the thing is with the plugin primitives is that you've got another hook there, right? You've got the interface to the virtual machine proxy. So you could put explicitly batteries in there if you wanted to. But so far. But I don't know, what do I use? I usually put coding in there. I'm really a bad tester. So I just think it's incredibly stable. People in the outside world use it. Oh, yeah. So, okay, that's how to work with primitives. And the cool thing is that I co-opt or extract plan. So the way that I discover the primitive access to depth for each primitive is by running the slang compiler to produce parse-trees and analyzing the parse-trees, looking for message stems which are object accesses. So it's all done through automatic analysis. I have to sit down and read every primitive and come up with a depth. It's all done automatically. The thing we see in the simulator, when the simulator runs, a plugin gets loaded and then a bit of the progress from the plan calculates the physical conditions that analyze the particles and keeps all of it and give access to depth. So, in the real VM, there's like a table for all of the number of primitives of the access to depth. If it's negative, it means it doesn't access 0 or more does, and then there's a column that hides the information in main. Okay, so that's how lazy forwarding works, and I hope that I'm running late. So, just to finish off, let's look at the memory manager. Has 3 main organs. There's a generation scavenger, there's the memory manager, which manages old space with free space, with compaction, scan bar, and then there's a segment manager, which has a tool. And I want to cover the ephemerons, the object representation, the thing I call compact, and then bridges, and then how do you debug this. So let's go through this. So I don't want you to read the slide. The important thing about this slide is that it's only like 1, 2, 3, 4, 5, 6 lines of code to figure out whether you can fire ephemerons in the scavenger. And if you look at the code in HDF, which took me, which I paused I was just prototyping it, making sure it worked, caused me to delay a release for 2 months, and still people who want to release it for doing that. It's bloody complicated. I'm convinced that this is correct. It's so beautifully simple and special. There's 2 versions, there's one in the old space collection, there's one in the new space collection. And it's very, very, very simple. It's never to do it in a high-level language. So the cool thing about this is with the tiny amount of code, you can express things at the right level of abstraction, and you can reason about the code. Okay, so when you have a flat object space, you will need to enumerate objects, for example, for all instances. When you want to go through all of the objects in memory and find each that has that flat. Our system each has a particular class of objects. So, here's the object representation. If there's less than 254 slots, so less than 255 slots, there's a byte which says how many slots we've got, there's a class, etc. We've got at least 1 slot. So this is pretty complicated. This is exactly it. And when we have an object that's 255 slots or more, we prepend the 464-bit word as a slot count. And then, so as we're working, when we step up to the end of one object, we set this byte, and it tells us it's 255, but this is a 2-word number. And it's less than 255, it's a 1-word number. It's very easy to parse this object. So, if you have a hammer, which is forwarding objects, you could say this as a nice way, like, okay, I've got this powerful feature, I can keep on using it. It's not really what's happening now. But yes, let's keep on using it. So, we need to compact the system. So, old space, and this is old space because the scavenger compact because it does its thing. First we've done a scan mark, we'll retain those forwarders we created. And the scan mark also follows forwarders to eliminate forwarders. And we may have reclaimed some objects, other operations. So we'll have some free space, and we'll have some objects. Our job is to move the object at the top of memory, straight to down. One way of doing it is to, the interaction point is to make a plan, and then we can squeeze things down. But I don't want to do that, because I've got the forward. So I try to use exact fits where you go for the objects at the top. Scan through objects and put them in a circular bucket, go through bucket backwards. Trying to look for exact fits to move objects down. It just didn't work. Instead, there's this greedy thing where it looks for space and moves as many objects as it can and keeps them on going. But if we're in the 64-bit system, we've only got 1 slot in our object that we can rely on in free space. So how do we access the objects at the top of memory? We can create this linked list through the free space. But we need to go down the free list backwards to find the objects at the top of memory. Because if we start at the highest three objects, we know that there's objects at the top that we can move down. Whereas a brilliant trick from years ago, which is that you can form a doubly linked list with one field, if that field holds the difference between the things on either side. So you can use either X or minus. And so if I know that this is the first object in the list, then the value in here is going to be the difference between 0 and this object. It's going to point to that object. So now I hold onto this object and I grab that object. And now I'm holding onto this object and I know that the next object is the difference between this and that. And then you have to have two handles which fix it. It means you can have a link between one field. So what happens is that the free space is stored to the same degree through this one field, and you discover the object at the top by traversing the list from the end and moving the object down. So in doing this, it's very, very easy to leave objects behind. So if there's a pin bit, a circle, as there is in that blue object in the second diagonal, we just leave it where it is. Undisturbed. And so after a compaction, right, we will have moved objects into free space down the bottom, and we'll have left forwarding points behind. So then we make a path through memory, follow all of the forwarding pointers, and then we end up with the situation where any pinned objects are where they are, and all of the free space is being used. And so, when the system snapshots, it goes through that process sequence. And this is something that we can incrementalize, in that if we have an incremental collection of yet to be added, we can do a small amount of compaction. And then instead we just move some objects. Okay. So, another part of the design, again, yes, right, is how do we do things? So, we saw that these large objects are things that have a select tag and a normal header. If we construct objects that the segment manager knows about, that the rest of the memory manager just wants a normal object, these are two-word objects which say, hey, I'm Brits, don't look at my content, it's full of arbitrary garbage that you don't want to look at, and don't move me because I'm Brits. And they lie about their size, they say, I'm big enough to get you to the next thing. And so that's what we've got here, those guys. So at the end of the segment, there's a keyword thing that says, actually, I'm big enough to stretch to that point of the distance. And so that turns a series of segments into one continuous object space, where when you walk the thing, the water just stretches over the distance. Okay, so this is really important. Choosing an abuse, how do you use like the garbage collector? Garbage collectors. So, about being objects, the question is how do you deal with functions? How do you deal with being objects doing functions? Because you want to store them in the file, right? Right, so you want to order them to get rid of the free space in between. Right, so unfortunately you end up with free space in the structure. And that could be large. And that could be large and it needs to be the very system. Okay, garbage collectors are structured graph rewriters, right? And after you've run a garbage collection, any of the old objects will disappear, and so you may not be able to figure out what's going on. And when it goes wrong, it's basically flat. So how do you deal with it still more length? So what you do in the simulator is put a deep copy of the entire VM and put a deep copy of the thing. And if it dies in a heap, then you can take another copy and you can step through and find out where it crashed, and you can repeat that process at any time. And if it reaches the bottom with grace, you walk off towards the edge of the system. So do the thing in the simulator. Lemons and buzzes and complex algorithms, like take a copy, get the copy to commit to its head, see whether it commits technically cleanly, and continue. Okay, so status. Performance, as they say, is all over the map. So, I initially claimed that this would be, make benchmark 40% faster, and then I went for backpedaled a bit, but people are having good effects, 50% speed up. And I have one snippet which goes through all of the subclasses of link which are used as global variables and adds an instance variable to it, which is like adding an instance variable to the association to it, which key value 3. It goes back to all of those. And then you move them to that place, lots of become a little bit of compilation, but only 6 times faster in Spur than it is in Cog. So there's some good speed-ups. So the functionality, the missing functionality is that I haven't implemented image segments yet, so we don't have Spur for employees, and for that, which usually is got segments of behavior, which is images, but that's no problem can be implemented. And the incremental collector is not going to be implemented, and I have no solution for three basic simulation because it's so availability, I just broke it last week. I needed to make a change. I give you a URL, but the images are appearing on my website. Miranda has supported my bootstrap to Pharo, and Squeak are working together to put together a Pharo image we hope to. But Elliot and I will be starting off 64 bits together. And so in the system, 64 bits hasn't been tested, even though all of the subclass methods have been written. So, there's a whole series of issues there. First of all, there's a Cog VM, which is 64 bits, which could be relatively trivial, but to do the trick, we also need an activity 64 backend, so there's some more work there. But we should be able to have 64 bits sometime next year. Thank you.
Elliot, you were speaking about Camelot. Does the thought you invented also apply to the one-way become?
Yes, how is that the same? Yes. Yeah, so I didn't demonstrate one-way become, but in one-way become, you say, okay, you take all references to this object by reference to that object, and that's implemented exactly by just making this object the forward extension to that object. I'm sorry, you do stand the back table, not in depth, because it's 0 level. So and Jeff's point was, surely I have to follow the back table so that when you do reference the class index, you get the class index. So that can be done immediately after become, you're only scanning the pages, you're not doing the classification. So that's what the point.
I meant more like to avoid one-way become from changing the cluster from object forcefully, that one-way become somehow is not how to affect the references pointed to the cluster.